Okay, so I was now taking a look at the stuff where I left it many days ago. It's been a bit of a longer break, but hopefully I can remember where were we with all these, right? So I was trying to record a session yesterday, but it just didn't work out. So I did a bit of these already, and I think the last stuff that I was working on was the batch size so that we can have multiple sentences in here. I'm not so sure if that's exactly what's needed for the input and the output embedding altogether. Like I'm still a bit lost in terms of like what will be the next best step, but I think that it should all work well, right? So you know we're doing the positional encoding stuff, and then we're doing the multi-head attention. This is where then the magic happens, as in like we're splitting the head, but that's fine. That's just the dimensionality of things, the depth. And then we're doing a what else are we doing then? Then we're doing the dot product thing, right? So essentially, we're creating. So we're initializing these Q, K, and V matrices randomly, and then we're doing here a projection, right? A projection of our encoding into these different, and then trying to see what the what relationships are there. So I guess, and my guess, and I think that's what I'd like to figure out now, maybe for the next step, is like how, um, what will be the best next step, right? So do we implement now sort of an actual training? You know what I mean? Like, how would the actual training stuff would look like? Like, because I just have sentences, right? But then essentially, well, you need to train on um, finding the optimal values for these Q, K, and V matrices because that's what's going to tell you, um, what projections are giving you the best information. Because that's the point, right? So the point of these is to say, I have this Q, K, and V things, and then I project my encoded input into these. Um, you know, is these, and then kind of you do that, then you basically compare this with whatever the expected output was. That's just my assumption, right? So, and you try to understand whether that, that specific projection is the optimal one, and then you adapt this projection. That's kind of my guess. So I think today it's just going to be mostly like 15-20 minutes to kind of try to figure out what the best next step is. If I recall well, I think these is working. So if I delete these CSV files, I think if I just run the thing, it should actually work. It creates these files, and if I open them, not like these, but I open them with the CSV editor, um, then I was getting the, oh yeah, so those are the attention, right? So that's what was like for sure not working well, right? As in like these guys over here should be empty because these things are just, um, and then, that's kind of okay. Like the and Fox have like a high attention. That's fine. But then it's like Quick, this makes no sense. You know what I mean? Like these metrics should tell you where is the attention placed, right? So, and now I want to make sure. So maybe what I'd like to see is if I can implement, because that's all I have. I have the multi-head attention mechanism. I'm not so sure about this feed forward piece in here, whether that is this dense step. There's a dense layer here that is used for what? Here. There's another, like, I don't remember what was this used for. I think it's just another layer of parameterization, right? But I'm not so sure if this is this feed forward thing, because it's just matrix multiplication. So my understanding is feed forward is actually a neural network. So I think we have really just implemented that little box here, the multi-head attention. So I guess now my question to Ghostwriter would be, how So is the voice is coming through correctly? Yeah. So how? Because I just have one screen today. How do we train the? Because there's two things, right? So on one side we've got. I don't think so. I don't think we need to train the positional encoding. We still need to understand how it works, but I don't think this needs to be trained. Because essentially this is computer positional encoding for training. So essentially, this is just something that you're encoding positions, right? So you're just encoding positions. That's it. Maybe there's more stuff we can do. I don't know, but that's just encoding positions. But then the actual magic happens here, right? So now the question would be Ghostwriter. So let's give Ghostwriter a bit of context, right? So we've got a basic positional encoding and multi-head attention mechanism or multi-head attention mechanism implemented. What are the next steps in order to train the Q key, the Q key, and V matrices so that we can find the optimal attention? Because there's still all these other stuff like there's still all these if I look at the architecture, right? This I don't. So there's still all this stuff with like the output embedding, which I I don't think I've. It's a variation of the multi-head attention because it says masked multi-head attention. So I might have to implement these. First, I'm not sure I understand this. I'm not sure I understand this as in like, is this the training architecture? I guess so, right? I guess. So what does Ghostwriter say? Next, you would typically define a loss function and use an optimizer to train the model. In case of multi-head attention, you would typically use a language modeling task to train the model. This involves taking in a sequence of tokens and generating the next token. In the sequence, you can use a cross-entropy loss function. I remember this loss function stuff. To use an optimizer, you need to define a training loop. In the training loop, you forward propagate the input through the model, compute the loss, compute gradients with respect to the model. I think, okay, so in general I know that, right? But update the model parameters using the optimizer. You repeat this process for multiple epochs until the model has converged to a good solution. Okay, that's fine. But what about these boxes? What about the output embeddings and masked multi-head attention? So context of a simple whatever you use for. Oh, that's interesting. This is using replit docs. Output embeddings and masked multi-head attention are important components of a transformer architecture used in natural language. The output embeddings or output layer in some literature refers to the final layer in the transformer network that maps hidden representations of input sequences to output classes or labels. This layer is usually a dense layer that applies. That's not our case. Masked multi-head attention, on the other hand, is supposed to compute the contextual representations of tokens in the input sequence. This computation is done with the help of the attention mechanism, which uses content-based attention in order to selectively attend to certain parts of the sequence that are most relevant to the given output sequence. Okay, so but then this means it's part of the training. So I'm giving the thing an input and an output, right? And I'm calculating the relevance of the input with respect to the relevance of the elements of the output. I think the masked part of the attention refers to the mask given to the attention mechanism when processing masked sentences, ensuring that each word can only attend to a limited set of words. This helps to avoid the possibility of the model seeing feature words in training data, which gives the model an unfair advantage during training. This helps to avoid the possibility of the model seeing feature words in training data. But isn't that what we really want? Overall, these two components of the term architecture are crucial for enabling it to learn the unlock patterns and protect natural language. Okay, so um, so how can I use my code in ManPy to also include the output, all my training data, so that I can train it? I'm not so sure if that's the right question. That's what I to include the output labels in your code. Ugh, labels. Okay, so now there's gradient, apply gradients, trainable variables. I want to do this as low level as possible. So I don't want to rely on existing stuff, even if that's just slow. To include output labels in your code, you first need to define your labels. For a language modeling task, your labels would typically be the next token in the sequence. You would then modify your code to output the labels during each training iteration. Here's an example of how you could modify your code. Okay, let's try to understand this. So labels. Okay, so I have this labels thing. I tokenize the words, tokenize the output labels, add padding to each word vector, cast the nested list on an array. That's what I'm doing. Create a positional encoding. That's all good. Create a multi-head attention layer. Apply the multi-head there. Okay, convert the output to logits by applying a dense layer. Okay, so this is the first thing that we're doing. So what are logits? Calculate cross entropy between predicted logits and actual labels. Okay, so that's the news now. Compute the gradients for trainable variables. Apply the gradients. That's kind of high level stuff. And then I guess you would just iterate on that, right? So convert the. I'm not so sure how that maps. Release down position encoding, output embedding, outputs shifted right. So what are logits? Logits are the raw unnormalized predictions that are associated with the model's final output. In other words, they are the outputs of the model that have not yet been transformed by a softmax function or any other activation function into probabilities. For example, in a binary classification problem, model might output a single logit, which can be interpreted as the model's degree of certainty that it belongs to one of the classes. The logit can be transformed into probability by passing it through an activation function. In the example earlier, I use a dense layer to convert the outputs of the attention layer into logits. The logits are then used to calculate the cross-entropy loss between the predicted labels and the actual labels. Okay. take the output. So the output is the, if I go here, the output is, what was the output? Compute the weighted sum of the value of tensors using the attention weights. Attention weights and V. I don't really see how is that an output. That's the first thing, because it's just multiplying the attention weights to the same inputs. Unless again, we have to here play with the fact that input and output should be encoded together. That's maybe what I should start to try to understand first. So let's go one step back first. How should I encode my training data set for a language for an LLM based on the transformers architecture? Is it that, so what does the training set look like in the first place? In my code, I currently just have a set of sentences. So to encode the training data set of a language model, based on you need first to pre-process the text by tokenizing it into smaller fixed length units called subwords or tokens. I mean, okay, so because I was kind of under the weird assumption that maybe it was about having pairs of text, like, you know what I mean? But it might just be, it might just as well be that this is all about having having just the text and then having a window that kind of goes through, you know what I mean? And then this batch concept is then even more confusing. So you need first to pre-process the text by tokenizing it into smaller fixed length units called subwords or tokens. That's done. The tokenization process splits the input text into a set of tokens that represent either individual words or parts of the words, depending on the specific tokenization algorithm used. Yeah, these tokens are then fed into the LM, which predicts the next token in the sequence given the prior context. Okay. In the transformers architecture, the input sequence is typically represented as a series of token embeddings, which are learned using the transformer encoder or transformer decoder layers. To train the LM, you need to provide it with a large corpus of text data. The corpus should be representative of the language and domain that the LM is intended to model. Each sentence in the corpus should be treated as a separate training example. Okay, so each sentence. So it's a bunch of sentences of text. So I think that'll be just fine. I guess when it comes to this masking, then it's just to kind of fake that sliding window. You know what I mean? Like first you just say the, right? And then you don't see anything else in your sentence. Okay. In your code, each sentence in the corpus should be treated as a separate training example. In your code, you already have a set of sentences which you can treat as your training data set. However, you will need to pre-process the sentences by tokenizing them into subwords before feeding them into the LM. That's done already. To tokenize sentences, you can use a tokenizer that is compatible with the transformers architecture. Some popular tokenizers As tokenizers, okay, this we can then do later as a sort of an improvement, right? But we've got like our tokenizing algorithm here. Once you have tokenized the sentences, you can convert them into token indices or embeddings that can be fed into the LM. Typically, the token embeddings are learned during training for the LM based on the distribution of tokens in the input text. Okay, that's what I'm not sure about. Convert them into token indices or embeddings. Finally, to train the LM, you can feed the tokenized and encoded sentences to the model. So you feed the tokenized sentences to the model and update the model's weights and using backpropagation based on the loss between the predicted and actual tokens. I guess I'm interested in this last loop. And the program, the learning. Currently, in the code, I have a tokenization in place, and then I've implemented the multi-head attention part. But I am not sure how how should I handle the iteration within a sentence. That is, how do I distinguish between input and output? And how do I loop through to actually calculate to actually improve the weights? This is the hard part of the thing. So you will need to feed your tokenized and encoded sentences into the model one at a time, and update the model weights using based on the loss between the predicted and the actual next tokens in the sequence. To do this, you can implement a loop that samples a random sentence from your training data set, divides it into chunks of fixed length. Chunks of the input the chunks represent the input and output sentences that your model will learn to predict. For example, you could split each sentence into overlapping chunks of. Okay, so that's a good example. So chunks of fixed length. The chunks represent the input and output sequences that your model will learn to predict. For example, you could split each sentence into overlapping chunks of length 128 with a stride of 64. This would give you a series of input-output pairs that can be used to train the model. Once you have your input-output pairs, you can feed them to the LM one at a time and compute the forward and backward passes of the model using the input sequence as the input and the target sequence as the output. Okay, so you're gonna have, for example, you know, the quick brown. So I can say like the quick brown and then the quick brown fox as an input. Okay. You can then compute the loss between the predicted output sequence and the actual output sequence, and use the backpropagation to update the model's weights based on the gradient of the loss with respect to the model parameters. In your code, you can replace the existing call to the attention layer with a loop that iterates through the input-output pairs. So we need input-output pairs. The loop should extract the input and the output sequences from each pair, compute the forward and backward passes of the model using these sequences, and update the model's weights based on it. You can use an optimization algorithm such as stochastic gradient descent or ADAM to take. So if a turns in my data set looks like this. How give me an example of input output pairs it can be split into. So the quick brown fox jumps to the lazy. Okay. Yeah. But in the current code, I'm calling MHA with my entire. So in my current code, I'm calling MHA with my entire input tokenized data. So I guess I just need to feed it the input parts and then use the output just for the loss comparison. Should extract the input sequence and the target sequence, where the target sequence is simply the input sequence shifted one position to the right. Okay, so we're getting something else in here. So for each input-output pair, you should extract the input sequence and the target sequence, where the target sequence is simply the input sequence shifted one position to the right. You can then pass the input sequence to the multi-head attention layer to get the model's predictions and compute the loss between the predictions and the target sequence. You can use it. This is still not clear. How do I do that? How do I get that? Okay, so in attention, so is in my code is the so in my code in attention.py is the function responsible for generating the predicted output. That's what I'm not so sure. How is that prediction generated? Because I get weights and that's it, and then these weights are applied. But what does this mean? You know what I mean? Like I kind of am missing like the actual predictive mechanism. No. Okay. Compute attention weights, exactly. The output of the attention function is a weighted sum of the vectors, which then undergoes further processing by the multi-attention layer to produce a final output sequence. Layer the implement takes the input sequence. So much of attention operations and nonlinear transformations, correct. The output of the layer is returned as a tensor of shape. Okay, then I'm definitely not really. So what is the number of sequences in the batch? Okay, I'll have to give a second attempt to these in the next session. Kind of running out of time right now. But essentially, okay, so essentially my next step is to try to figure out where am I actually getting a prediction and where can I feed in this kind of comparison? Because that's not clear to me. So it's definitely not clear to me. I just have a bunch of sentences. And so far, the code just calculates the attention. I don't know what this applied attention thing is really, right? So this is just yep. Anyway, think, yeah, I don't know. We'll see. I think that is basically the problem that I'm having right now. So I don't know really when the whole dot product attention thing happens, you know, like the attention weights, this output, these compute the weighted sum of the values. This is not the output. That's my promise. I don't really know what is going on here. That's definitely not like. So I'm missing how to calculate the actual output, the actual prediction. I'm missing how to calculate the actual prediction. Yeah. How to calculate the actual prediction. This is kind of the next step, I would say. It's definitely not this output. I don't think so. That's what I'm missing. Cool. See you next time.